Okay, welcome back. We were discussing about the noise figure and the noise temperature and their relations, and we will see the relations, how it is happening with a device which is amplifying, having some gain G or loss. The G is negative in that case. Okay, let's write it. That is for active device. In this case, I mean it has a gain with gain of G. You can write it this way. That is a amplifier, and gain is G in dB, and noise figure we write F in dB, capital F. Earlier I was using capital F always, just to distinguish. Will convert into small nf. I am writing noise figure. This is in ratio, just to differentiate. Normally these are the nomenclature people use. So, capital F is normally in dB and denotes the noise figure. When it is converted into ratio, I am writing as a small nf. So, F is equal to 10 log of 1 plus T e by T 0. Since it is 10 log, this is in dB, and noise figure in ratio will be simply 1 plus T e by T 0. Earlier we have said this one as capital F, just to make sure that you do not make any mistake. That is why we are calling it as NF, that is ratio, not in dB. Don't confuse. When it is ratio, the temperatures are simply numbers in ratio, so T e by T 0. When it is in dB, it has to be 10 log of that. So, this active device with a gain G can be equivalently drawn as if there is a, I am drawing the same thing what we have discussed earlier, that is there is a input with a noise temperature, effective noise temperature T e, which is equal to T 0 n f minus 1 in ratios, and a noiseless amplifier which is a gain G. This is noiseless, as if the noise is coming from the input, and there could be some input temperature that is coming in, and this will be the output. Now, let us see that how do we represent the same thing for lossy device. Which is lossy device or network. Let us normally we denote it by resistance, and there is a power which is coming in and power which is going out. So, loss, or many times we say attenuation. So, that is why it is denoted by A, it is in dB, and the same thing when I write in ratio, called small l, which is ratio. Now, this can be equivalently drawn as the similar way. At the input, there is a T e which is equal to L minus 1 into T 0, and there is, I can call it an amplifier with a gain which is equal to 1 by L, as if the noise is generated as the input part, and this is noiseless amplifier. So, L, small l, is the called loss factor, which is P I by P O. The A is the 10 log of L, and obviously the gain also you can say gain in terms of ratio G is equal to 1 by L. I have written small g for ratio, which is 1 by 10 to the power a by 10, 10 to the power minus a by 10, various ways you can represent the whole thing. The issue what I am trying to point out is we should use, when we go into the temperature, we should use a number which is a ratio, not in dB. So, attenuations are defined in terms of dB many times, convert into number which is a ratio, and then go into the temperature, noise temperature calculation. And it is same as the noise figure. In case of gain, with the gain of an active device, you have seen this was the noise figure, and in case of a lossy device, it is the loss in ratio. This you have to remember, because we will come across in many places there may be loss or gain. But before that, in our total system, we have seen that there will be various stages, like we have seen that there is a LNA, then there are down converter, then there are amplifiers. So, many systems are cascaded, each of them may have different gain, different effective noise temperature, and maybe different bandwidth also. So, let us see in the cascaded system totally what should be the system noise temperature that may arise. Let us look at a two-stage cascaded system. Say first stage we call, let us say it is having a gain G1, it has a noise figure F1, it has effective noise temperature TE1, and it is cascaded, that is connected to another system which has a gain G2, noise figure of F2, effective noise temperature of TE2. These two are cascaded, where there is a noise power coming input in I with the temperature of normal temperature of T0, and this goes out as a noise power NO. So, for the first stage, the output noise power, let us call N1. First stage is output is N1. Let us say this whole thing in a equivalence we can put as a one single unit, which has a gain of G1 into G2, which has a noise figure which we call F cascade, and which has a effective noise temperature TE cascade. Is the equivalence of that, which has similar noise power as a input and effective noise and a temperature T0 and a noise power as a output NO. So, we can write N1, which is intermediate stage from the first stage, is G into K into T0B, and then of course each of them has bandwidth B, both of them same bandwidth, plus G1 into K into TE1 B, its effective noise temperature, its own temperature is added. Then N0 is G2 into N1 multiplied by G2 plus its own, that is G2 K TE2 B. So, this is the output of the first stage, which is the input multiplied by G1, input noise multiplied by G1, and its own noise which is generated based on effective noise temperature, and output of the second stage is input from the first stage multiplied by the gain of the second stage and its own based on its own noise temperature TE2, whatever noise power that is generated. Now, if we expand these two, the N0 is G into K T0 B G2 plus G1 into K TE1 B into G2, that is from the first stage, and then G2 K TE2 into B. So, if we take as a common G1 and G2, G1 and G2, and then of course K and B are there. So, only in temperature it will be T0 plus TE1 plus TE2, here G1 is not there, so divided by G1. Now, this one is the equivalence we have said that total G. So, this is G into K into B, and this one we can say T E cascaded. So, then it will be T0 plus T E cascaded. That means T E cascaded is equal to TE1 plus TE2 by G1. And if we look at the overall system, let's call it system noise temperature, with term is a TS, which is that input noise input temperature, which is T0 we have assumed, plus TE cascaded. So, that is the system noise temperature. Now, we can convert the whole thing from noise temperature to noise figure. So, replacing TE cascaded with F cascaded minus 1 into T0, we will get that F cascaded minus 1 into T0 is equal to that F1 minus 1 into T0 plus F2 minus 1 into T0 by G1. So, that gives F cascaded as F1 plus F2 minus 1 by G1. And we have earlier seen that TE cascaded is TE1 plus TE2 by G1. So, this shows important thing, that is the first stage noise figure. To reduce the total cascaded noise figure, first stage noise figure should be low and it can have a moderate gain. So, that second stage noise figure will get reduced since it is divided by the gain. Same thing, the first stage noise temperature should be low and second stage noise temperature is not that critical because it is divided by the gain. So, first stage gain can be moderate to high. So, first stage noise temperature should be low, that says this should be low noise amplifier, and the low noise amplifier gain should be moderate. If you remember, in our space system we have said that LNA gain is roughly of the order of 2 dB, 20 dB it is kept, and subsequent gain can be higher. That particular LNA has to have low noise temperature or low noise figure. Now, with this certain important aspects that come out, and that can be seen if you try to solve this particular example. I will give you an example. I won't solve it here, but I will try to put the problems in front of you, so that you can solve and you can find out what are the different interesting part that comes out of it. Let us say that there is a from the antenna, I mean, let us exclude the filter for the timing, and we have, this is antenna. So, it is giving some temperature, let us say Ti is the input, or Ta is coming from antenna, and this is the RF stage, which is nothing but LNA, we will see. And then after that there is a stage which is nothing but the mixer, then LO, then filter. Try to recollect our space segment diagram. So, this is the this is called down converter. Then the down converted thing has to be amplified by a amplifier, which is IF amplifier. Now, selection of the gain and noise temperature of each of them, assuming all of them operates in same bandwidth, is very important. Now, I will try to pose a problem, a couple of problems with different numbers by changing their gain and temperature, etc., and you will find the effect of that, how it is coming. So, let us say for this is example, for a receiver input noise temperature is 25 K. Remember, it is not T0. Then RF amplifier noise temperature is 50 K, low noise, you can see, and RF amplifier gain is 23 dB. Then down converter noise temperature, when I say noise temperature, is effective noise temperature, is 500 K. You can see that low noise amplifier was having much lower. The second stage I am having much higher noise temperature, and the down converter gain is 0 dB, it does not provide any gain, let us say. And then IF amplifier noise temperature is, let us make it very loose, 1000 K, and IF amplifier gain is more, 30 dB. Now, find, first problem is find receiver system noise temperature. When I say system noise temperature, you have to find out that equivalent noise temperature of these 3 subsystems in cascade and add the input noise temperature also. So, that gives you system noise temperature. You will find, you will get some number, and if you look at this number, it looks quite practical. That is, initially noise temperature of LNA is low, subsequently a little higher, further higher, initially moderate amplifier gain, down converter is 0 dB, IF gain is much larger. Now, what happens that if the down converter gain reduces, actually it is a loss, because the filter is there, mixer is there, that is lossy. So, second stage you find receiver system noise temperature when down converter gain is minus 10 times low, minus 10 dB. And then what is the effect of this? Much more important is, now this gain is reduced, but the effective noise temperature is mostly dependent on the gain of the first stage. Some effect of the second stage will appear. So, a little change you will find. You will find more changes if we change the RF value, receiver system noise temperature, when the RF noise temperature, RF stage is equal to 200 K. Instead of 50 K, I am increasing it to 200 K. You will see the effect. As it is, we know that if this noise temperature is high, the effective noise temperature of total system will be high, because this plus second stage divided by gain of the first stage plus third stage noise temperature divided by the gain of first stage and second stage, like that it goes. But here you will find with numbers. And then let us go back to that RF gain and noise temperature, RF noise temperature same, that is, find receiver system noise temperature when RF noise temperature is, go back to the 50 K value, and RF amplifier gain is increased 50 dB. Earlier it was 23 dB, I increase it to 50 dB. Then what is the effect? You will see, obviously from here we can find out that the first stage, the effective noise temperature, we maintained the same value as 50 K. The second stage was reduced by the gain value of 23 dB initially as the first problem, and in the last problem we said the first stage gain is increased. So, this noise temperature will be reduced by this much gain. Remember that these calculations, when you do, you are doing on the temperature. So, therefore, the values what you are going to use for gain, which is given in dB, has to be converted into numbers. So, do it in numbers, and then you will get finally the temperature value in degree Kelvin. You can call it a dBK later, converting back to the dB. So, with this very briefly we have gone through the noise temperature and noise figure, and let us try to recollect some of the important issues what we discussed till now. That is, initially we have said that the power is important aspect of our link budget. So, we transmitted the power from a isotropic radiator with PT, and as the distance increases, the power flux density reduces by the ratio of distance square. And then instead of isotropic radiator, because the distance is very large in our satellite communication, the losses or reduction of the power are much more. So, therefore, we focus with an antenna having gain, and then we have come across a term which is focused power, which we call effective isotropic radiated power, EIRP, that is the transmit side characteristics. And on the receive side, we have got the receive antenna aperture, which also determines the gain of the receive antenna, and because of the distance the losses are happening, it is called path loss. That was a very basic thing. But then subsequently we have seen that there may be many more losses if the transmit and receive antenna are not properly aligned to their bore side. There will be depointing losses from the transmit side as well as receive side antenna. There between the power amplifier output to the antenna point, there is a there are cables and other systems are there, which we call feeder loss. Similarly, at the receive antenna to the receiver, there will be certain feeder loss. So, transmit and receive feeder losses are there. Then there are the path losses, which we have already seen depend on the path, which some people call it free space loss. But in addition to that, there may be atmospheric losses. Details of that we will discuss later. There are some losses. And then there are certain polarization losses if there is a polarization mismatch between transmitter and receiver antenna. So, with all these losses, we will get some power. Then we discussed about the noise, how in any real practical device which is not at a temperature 0 degree Kelvin generates noise, how it can be modeled, and then effectively we said there is a physical temperature, but then there could be effective noise temperature, which is as if it is a resistance having a particular temperature generates that amount of noise, which is equivalent to that particular circuit, which may be amplifier or it may be lossy device. So, we have got effective noise temperature for each of them, and it is equated to Boltzmann constant, the temperature and the bandwidth. And there are certain assumptions that this assumption works in the frequency range of microwave and normal temperature. And subsequently, we have seen another characterization which is called noise figure, relation between noise figure and noise temperature we have seen. And then we have tried to cascade different systems and try to find out what is the total equivalent noise figure or equivalent noise temperature. And one caution always we have seen that when you try to do calculation, it is better to do it in noise temperature range, and you do it in ratio. All numbers which are gain or noise figure which are given in dB, convert them into ratio, and then you calculate. And we have tried to see in this the first stage is very important, its noise temperature, its gain is very important, which affects the total system noise temperature or noise figure. And there may be certain input noise temperature, or if there is a noise figure assumption, then better you do it as if the input is matched with a temperature, normal temperature T0 is 290 degree K. And we have given you some examples and problems which you should work out yourself to get the numbers and understand what we have discussed till now. Okay, thank you very much till now, and then we will continue our link budget discussion in more detail based on antenna, the ratio of carrier to noise, etc. Thank you very much.